So let's let x and y be sets. So they could be sets of numbers, something like the real numbers, or they could be sets that are not numbers at all, something else entirely. For example, x could be the set of cities around the world, and y could be the set of countries. A function, or a map, assigns to each member x in the set x a value f of x in the set y. So each member of the set x is assigned something in y that we call its value under the function f of x. So, for example, if we had a set x with just 3 elements, we could have a set y that has 4 elements, and we could send the first 2 elements in x to this element to this element, and this is some function f between these two sets, x and y. To take a different example, we could have a function, oh sorry, I should have said a function f from x to y. So we could have a different function from the set of cities to the set of countries, such that f of a given city is the country that city is in. So for example, f of Paris would be France, f of Beijing would be China, and f of San Diego would be the USA. So this is a completely different kind of function. Now these two sets x and y have names. X is called the domain of the function. This is the set of all possible inputs, and y is called the codomain. And notice that y doesn't have to be the set of all possible outputs, because notice in this example here, these two elements in y, nothing in x map to them. So it is not necessarily true that everything in y is an output of something under the function, but the domain is the set of all inputs. And inside y, there's a subset of y, in that case these two elements, called the range. The range of the function is the set of all possible outputs. And this is part of y. This is a subset of y. It might be all of y, but it might not be. So a different way to write this down is it's the set of f of x such that x is an element of x. So if we think about some more familiar functions, if we think about, example, the function from the real numbers to the real numbers, given by f of x equals x squared. Then the domain is this set here. It's the set of all inputs, so the domain is all of the real numbers. What is the range? Well, the range is the set of all possible outputs. But we know if we square something, it's never going to be negative. So the range in this example is going to be the interval 0 to infinity. This is the set of all possible outputs. And remember this notation, remember interval notation, an open interval like this with round brackets means the real numbers x, such that x is between a and b with square brackets. This is a closed interval. It means it also includes the endpoints. So another way of saying this, people sometimes write f of x is greater or equal than 0. That's another way of saying that the range is all of the non-negative numbers. So that's how to think about domain and range of a function. Just coming back to this mapping diagram, we can have a couple of different things that happen with diagrams like this. Obviously, it's only practical to represent sets in this way if they have a small finite number of elements. But just to illustrate an example of something that is not a function, so this is something that is not a function, let's consider something like this. So what's wrong with this? Is it a problem that these two elements both map to this? No, it isn't, because up here we had two elements that both map to the same thing. Or if we think about the function f of x equals x squared, f of 1 and f of minus 1 are both the same thing. So that's okay. The problem is this element maps to two different things. That can't happen. In the definition of a function, we said f assigns to each x in x a value, only one value. Perhaps we should make this even clearer and say just one value, f of x in y. It can't have lots of different values. So this is not a function. If you have something like f of x equals plus or minus root 4 minus x squared, this is also not a function, because this is ambiguous. We don't know what f of 1 is. Is it plus root 3 or minus root 3? It's not clear, so this is also not a function. I suppose I should also specify the domain and codomain. Really, whenever you give the definition of a function, you should say what the domain and codomain are. But yeah, these are some examples of things that are not functions. And now we come on to different types of functions. So one important type of function is something called a one-to-one function, or an injective function. So the terminology used in the book and in the exam is one-to-one. What this means is that we have a picture that is something like this, where each thing in X is assigned to a distinct element of Y. So no two elements in X map to the same element of Y. No two elements in X map to the same element in Y. That's what a one-to-one function is. Okay, and then we have a many-to-one function. So this is a function where we do have at least some pair of values that map to the same element in Y. So for example, here this is an example of a many-to-one function between these sets X and Y. Okay. To give some examples of one-to-one and many-to-one functions, a simple example of a one-to-one function would be the function from R to R, the real numbers to the real numbers, given by f of x equals x. Or f of x equals x cubed also works. An example of a many-to-one function would be something like f from the real numbers to the real numbers, given by f of x equals x squared. Because now minus 5 and 5 have the same image under this function f. So there are two things that map to each element in the range apart from 0. Now let's consider this question about finding the range of the following functions. So firstly, the function f of x equals 1 over x squared, where x is a real number that's greater than 0 and less or equal than 3. So this is the domain of the function. So the domain is not all of the real numbers, it's restricted to this half open, half closed interval between 0 and 3. So often with questions about the range, it can help to think about the graph of the function if you know what it looks like or are able to sketch it. So in this case, f of x equals 1 over x squared. Well, as x gets closer and closer to 0, 1 over x squared gets larger and larger. So we get something like this, where there's an asymptote, the y-axis is an asymptote to the curve. And then the end point, so notice the graph of this function is not the whole graph, it ends here at this point when x is 3. So you have to be careful about questions that involve sketching this, because the sketch is not the entire graph of the function 1 over x squared. So when x is 3, y is 1/9, 1 over 3 squared. So the range is all of the possible y values that the function takes, which we can see is everything upwards from 1/9. So the range of f in part A is 1/9, comma, infinity. It's all of the values that are at least 1/9. Other ways you can write this, you can say f of x is greater or equal than 1/9. That's often how people write it. Or you can say y is greater or equal than 1/9. Note that you cannot say x is greater or equal than 1/9. If you do that, then it will be marked incorrect in the exam, because it's not values of x, it's values of f of x, the function. The range is values the function can take. Okay, now let's see the second part. So this is slightly more complicated. Again, you have a slight advantage if you have a graphical calculator, because then your calculator can draw the graph of this function. But it doesn't matter if you don't, because we can work it out anyway. So notice this time our domain is numbers, real numbers greater than 1. And notice when x is 1, this function is going to have an asymptote, because the denominator would be 0. So we know there's an asymptote when x is 1. And if we put in values very, very close to 1, for example, if we work out g of 1.1, on the top we would get 2.1, and then we get minus 0.1, which is minus 21. If we work out g of 1.01, we would get 2.01 over minus 0.01, which is minus 201. So these values very close to 1 are becoming very large negative numbers. So that kind of suggests that where we have this asymptote at 1, the graph is doing something like this. But we don't know where the horizontal asymptote is. So what happens when x gets larger and larger? As x tends to infinity, the top is 1 plus a really large number, and the denominator is 1 minus a really large number. So we have, so for example, if we were to work out g of, I don't know, 10,000, we would have 10,001 on the top over minus 9,999. And we can see this number here is very close to minus 1. And as you put in really large values of x, you'll find that g of x is really close to minus 1, which kind of suggests that this horizontal asymptote in the graph here is at minus 1. So the range of this function is the possible y values. Well, it's everything less than minus 1. Those are the y values that this function can take. So the range is y is less than minus 1, or g of x is less than minus 1, or in set notation we can write minus 1, comma minus infinity. That's the range of this function g. Now we move on to piecewise functions. So a piecewise function consists of different cases that are specified. So for example, consider this piecewise function from the real numbers to the real numbers, defined by these two different possible cases. When x is less than 1, we say that f of x is 5 minus 2x, and when x is greater or equal than 1, f of x is x squared plus 3. So we're asked to sketch y equals f of x and state the range of this function f. So the graph consists of two different parts. When x is less than 1, we get this line, y equals 5 minus 2x. So if we were to put 1 into that, we would get 3. So the line, it's like this, and then it ends at 3 here. And this is 5. And then we have y equals x squared plus 3. Well, when you put x equals 1 into that, you get 4. So then up here at 4, we get this parabola. So this is an unusual looking graph. So this starts at 4, this line ends at 3 and crosses the y-axis at 5. And this is the graph of the function y equals f of x. So we're asked what the range is. Well, notice it can't actually take this value 3 because x is less than 1 in the definition. So the range is going to be, it doesn't include 3, but anything bigger than 3 is in the range. Or if you prefer, you can write f of x is greater than 3 or y is greater than 3. Any of these answers is acceptable. And then part B, solve f of x equals 19. Well, if you think about this graph, there are two different ways it could be equal to 19. There are 2 points of intersection with the two different parts of the graph. So either the line, 5 minus 2x, could be 19, or we could have x squared plus 3 is 19. And if we solve these, this one becomes x equals minus 7, and this one gives us x squared is 16, so x is 4. And x can only be 4 because x has to be at least 1 to use this part of the graph. So therefore the solutions are x equals 4 or minus 7. There's just one last piece of notation we need to cover, and that is if a function doesn't have to be written down in the form f of x equals something. There's some different notation you can use to specify a function. Instead of writing f of x equals x squared, you can write f colon x and then this arrow with a hook, x squared. And this symbol here in the middle means maps to. So f is the function that maps x to x squared. So that's some other notation you have to be familiar with.